talked about the idea of rotational dynamics, and now I want to take a moment and do an example of rotational dynamics. So let's do a drawbridge problem. Got a bar like this. Let's put the axis in after the bridge autocorrects. And we'll give this thing a mass of 10 kilograms and a length of 2 meters. It's a model drawbridge. And then we're going to put a car on here, very boxy car. We'll give that 2 kilograms, and we'll put it half a meter from the end. And maybe this thing had been pulled up by a rope like this, and it's connected to a winch, and that winds. And I'm going to say the rope breaks. When the rope breaks, this whole thing is going to swing down. So I would like to find the angular acceleration when the rope breaks. And I mean like right when the rope breaks. Once this thing starts moving, we're going to get a differing angular acceleration. So if that's my bridge, I'm going to start this thing at an angle of 30 degrees. Here we go. First, the forces acting on this, I'm going to have at the center of mass of this whole bar, which is about there, I'm going to have gravity acting. So there's my mg, capital M-G. Then I'm also going to have gravity acting at this location. There's my lowercase m-g. I would have tension going this way, but the rope broke, so no tension. I want to find the angular acceleration, so I'm going to need my torque equation. The sum of torques acting on my object is equal to moment of inertia times angular acceleration, and I'm looking for angular acceleration, so I'll just put that in red now. To get my torques, I need to look at these forces. Now I do have a set axis here, so there's no guesswork. So I do need to find where these forces are acting. This first force is acting at a distance of 1 meter from the axis, and the second force is acting at a distance of 1.5 meters. I'm going to have to break these forces into components, so let me do that. This one has a vertical component and a horizontal component, or maybe the better way to say it is a perpendicular component right here and a parallel component here. And this one, same thing. Perpendicular component, parallel component, and my angle. When I say perpendicular and parallel, I mean to the perpendicular or parallel to the line that connects the location of the force to my axis. Now my original vector, mg, is what I'm breaking into components, so that has to be the hypotenuse of my triangle, and I can find some sides. I know I don't actually care about these parallel components, so I'm not going to bother finding them. This one's going to be an mg cosine theta. This one's going to be a lowercase mg cosine theta. I'm going to need a direction to be positive. I see this whole thing rotating this way, so I'm going to make that my positive direction, because then everything's going to be positive, and that's convenient. Alright, here we go. So my sum of torques is, I'm going to have an mg cos theta and that happens at a distance of 1 meter. I'm also going to have an mg cos theta from this one, and that's going to happen at a distance of 1.5 meters because that's how far I am from the axis. Cool, that's my sum of torques. I'm looking for angular acceleration, so what's left is moment of inertia. I need the moment of inertia of this bridge system. So I have the moment of inertia of the bridge itself, plus the moment of inertia of the car. For the bridge itself, that's going to look like a bar with the axis passing through the center, so that's going to be a 1/3 ml squared. For the car, that thing's acting as a point mass, so m times, I suppose I can call this distance d, or little r. I'm going to call it little r so that I don't mistake anything for parallel axis theorem. M times r squared. So 1/3 times the mass of the bridge, 10 kilograms, times the length of the bridge, 2 meters squared, plus 2 kilograms times 1.5 meters squared. And I put all that in and I get 2.25 times 2 is 4.5. This one comes out to be 4.5. 2 squared is 4 times 10 is 40 over 3 is 13.3 kilogram meters squared. So when I add those up, I get 17.8 kilogram meters squared. When I put in my sum of torques, up here, I'm going to get 10 kilograms, 10 meters per second squared, cosine 30 degrees, times 1 meter, plus, there we go. First one, 10 times 10 is 100, cosine of 30 is 0.866 times 100 is 86.6 Newton meters. And here I'm going to get 2 times 10 is 20, times 1.5 is 30, times 0.866 is 26.0. So I get a total of 86.6 plus 26 is 112.6 Newton meters. And now I'm ready to go. My sum of torques is equal to I times alpha so my alpha is sum of torques over I. I'm going to get 112.6 newtons over 17.8 kilogram meters squared, and that gives me 6.3 radians per second squared. If I wanted to find the linear acceleration of maybe the center of mass of this thing, or you know what, of the car. If I want to find the linear acceleration of the car, I'm going to say that's equal to r of the car times alpha. So I'm going to get a 1.5 meters per second squared times my 6.3, 1.5 just meters, times my 6.3 radians per second squared, and that's going to give me 9.45 meters per second squared. That car, in the moment, is going to be accelerating at close to gravity, but not quite. As this thing starts going farther, it's going to be a little closer and a little closer to gravity until this bar is horizontal. When the bar is completely horizontal, then there's no longer anything holding this car up. so then its acceleration is going to be just straight gravity. That's it. That's how I'm going to use angular acceleration and torque and moment of inertia to be able to solve rotational dynamic questions.